Dear participants from all over the world, welcome to this webinar organized by Deltares Netherlands. The topic of the webinar is Ocean Modeling and Early Warning System for the Gulf of Thailand. We will start with a duo presentation by Koen Jan and Joe Rego. At Deltares, Joe Rego is one of our experts in the field of marine and coastal modeling. He is also our project manager for Clean Bay Services. Koen Jan is an expert in the field of flood forecasting and early warning systems. The presentation will take about 45 minutes. During this presentation, you can ask questions via the chat box. We will try to answer your questions immediately. After the presentation, you are kindly invited to ask questions by speech. I now give the floor to Joe Rego.
Hello everyone, this is João Rego indeed. Welcome to the webinar about the FEWS Gulf of Thailand project. The official name being Ocean Modeling and Early Warning System for Gulf of Thailand, an application of 3 software packages, Delft-FEWS, Delft3D Flexible Mesh, and SWAN. You see 2 names on this first slide, my own and Koen Jan. We will both give the presentation today, although this was a teamwork, so quite a large team both in Delft, Deltares, and in Bangkok from HAII. I want to give a warm welcome to all of you guys joining, especially those in Asia and Australia, who may now be in your pajamas listening to this presentation. I'll start. I have a few slides to interest you, so they give a summary of what we will show you and why this is so interesting. We'll talk about the development and implementation of a new early warning system that predicts coastal flooding levels along the entire east coast of Thailand. This early warning system provides 3-day forecasts. They are generated daily, and they combine the flooding effects of tide, storm surge, and wave setup. This system is based on Delft-FEWS and on open source software Delft3D Flexible Mesh, and also on SWAN. The early warning system is now used by the Hydro and Agro Informatics institutes in Bangkok to disseminate coastal predictions. And we'll show you here below a satellite image of a cyclone in the area, and also how these forecasts are now used for dissemination. Why was there a need for early warning system in the Gulf of Thailand? Well, this region is affected regularly by tropical storms or by the remnants of tropical storms. About once per decade, there's a very strong storm affecting this part of the world. And there was the need, especially given the recent development along the coast, both in terms of increase of population and infrastructure, and then also you have issues related to increased rainfall and climate change. This led to a clear need for such operational forecasting system, and we list below the main objectives. We wanted an automatic system to provide daily accurate tide, storm surge, wave and wave setup estimates. These are produced with a 3-day forecast horizon based on the latest regional meteorological prediction every time. And this is adding to the existing products by HAII, which they already covered fluvial flood forecasts and other natural hazards predictions. How did we achieve this? We achieved it by combining several modeling packages. So I'll stop here in this. I'll start with the top left. We use forecasts from the meteorological model WRF, quite fine, applied in this region by HAII, so 9 by 9 kilometer horizontal resolution. This runs twice a day, I believe. And then we used also fine resolution wave model, regional and local. The local model as fine as 300 meters along the coast. We also developed new for this system a hydrodynamic model with a flexible mesh. It's here on the bottom right. So we cover the entire southern part of the South China Sea, but we, being flexible mesh, we still go as fine as 250 meter resolution along the coast. On the bottom left, you see illustration of such a grid. You can have coarser grid where waters are deeper or where there's less features to simulate, and you refine along islands or the coastline. A small teaser in my first few slides. this is the kind of animations that you can obtain in such flexible mesh model. This is the upper Gulf of Thailand during a storm event, and what we're seeing here is both tide and surge in the hydrodynamic model result. And you see after a few hours in this simulation, you get well, a storm and higher water levels affecting Bangkok and that region. How did this come to be? This was a teamwork, as I mentioned before, a joint development between Deltares in the Netherlands and HAII in Thailand. As a project, well, I'll start with the people. You can see our photos on the right. Both us visiting Bangkok and the Thai guys visiting here in the Netherlands. A few visits occurred from side to side because this kind of project, it really gains from this kinds of exchange and on-the-job training. As a project, there were two major phases. One last year, just to give you a notion of the kind of timeline such a project goes through. Last year, around 10 months that were to develop and implement the system. So yeah, Deltares led the D-Flow FM modeling development and the FEWS component. HAII led the SWAN modeling. And today, actually since the beginning of this year, now the early warning system is fully operational in Thailand, and they are autonomous in this operation. For illustration, I also include in this slide some similar projects we did recently with the same type of software. So the three projects on top, they are operational, so everything runs automatically using FEWS. And the three in the bottom, they are not operational, so it's, let's say, detailed studies, also including Delft3D FM to simulate storm surge and tide. But as you can see, we do several projects with typical content like this with the same software. This is not an outlier. I will go briefly on the three software packages that we used. First, I'll describe Delft-FEWS. This is the operational platform that we use in many similar projects to provide operational forecasting. The acronym FEWS has historical reasons. It stands for Flood Early Warning System, although these days it's used for many other topics, not only flooding, other types of forecasts. You can use this for water quality, yeah, for many other sediment transport even. So this is the software that we use to make all the modeling and the data inflow, outflow automatic. You can see more on the link there from the Deltares open source software on the internet. To develop the hydrodynamic model, in this case, we use the recent Delft3D Flexible Mesh model suite. So this is the successor of the Delft3D4 model suite, which most of you probably know, or maybe you know both already. It's been around for quite some years, Delft3D4, and it's now being gradually replaced by the Flexible Mesh, the younger generation. This model is capable of doing 1D, 2D, and 3D model simulations, and it really allows you to optimize, by being spatially varying resolution, allows you to optimize high resolution, but at the same time obtain reasonable runtimes. And you also have the link there for the open source software website from Deltares if you want more information. Last but not least, we also use SWAN, developed here by our neighbors at the Delft University of Technology, also open source. We use this to simulate wave propagation and generation, but also wave setup, as I will discuss a bit later. So SWAN is quite handy for these kinds of applications in coastal ocean and then coastal setting. It represents many of the most important wave features: shoaling refraction, white capping, bottom friction, and depth-induced braking, etc. In this presentation, I won't spend too long describing the SWAN application, just because, we have to be efficient, and we'll focus in the hydrodynamics and FEWS configuration. Of course, you can always get back to us or check the website that I mentioned there for more SWAN information. This sketch illustrates how the different components are fitting in this early warning system. you can see that everything starts on top with a numerical weather prediction, which will force all the models. On the left, I show the wave models, which in this project were the development was led by HAII. So there's a regional model, coarser, forcing a local model, finer and focusing on the southern part of Thailand. And then on the right, I have the workflow with a hydrodynamic tide and surge model, which in this case, using flexible mesh, it's a new regional to local model. And then as you work down this sketch, you get to Delft-FEWS that combines all the workflows, including importing and exporting data and combining all the model runs. And of course, providing the visualization for the FEWS user. How do you go about developing such a hydrodynamic model? You want an efficient, fit-for-purpose model. So here I state again the main objective of the hydrodynamic model. We wanted to simulate coastal water levels accurately, and I might add efficiently, since it's an operational system. So we use Delft3D Flexible Mesh here in 2DH mode. So that's two-dimensional in the horizontal, thus depth integrated, which in this case gives us the added benefit of being very, very fast. And we want a fine resolution along the coast. So for this purpose, we wanted to simulate these 8 mechanisms that I mentioned in the slide. We want to capture tidal propagation, let's say from outside the domain. We want to simulate tidal generation by explicitly determining tidal generating forces. We want to simulate surge propagation from outside the domain, but also surge generation by wind inside our model domain. We want to capture all the effects of spatially varying meteorological fields. We want to capture both large scale and fine scale. So we want to capture very large parts, geographically speaking, but also much deeper waters. But we want to get to the detail of the small islands along the Thailand coast. And we want to, of course, simulate wetting and drying, since this is a storm surge model. This slide gives an overview of the typical data sets that you require for such a model development. Here I mentioned both hydrodynamics and waves. You see the similarity. Basically, you need the data sets for model setup. So you want to start with your shoreline information, also bathymetry fields. Then you need to define the forcing. In this case, I'm following on the left hydrodynamics. You need tidal constituents at the boundary, but also at the surface meteorological fields. And then you want to have data for calibration and validation. So you should gather, well, in this case, time series of water level at several locations. But if you can get your hands on literature showing co-tidal charts, that's also quite handy. For the wave model development, it's quite similar. Of course, the kinds of parameters you need to force the boundaries are different. The kinds of parameters you use for validation, it's also wave related. So this was the case in this project, but it's actually very typical in hydrodynamic and wave coastal ocean modeling projects. So I'll start by illustrating, in this case, the kind of thinking we put on which shoreline to use. In the end, before you go to actual model development, you want to have one land boundary, but this may be combined of different data sets. In this project, we use 3 data sets that we merged into one set. We use the NOAA global data set for the other countries, let's say. We use the local Thai land boundary, which is very detailed for the entire coast of Thailand. You can see there on the top right in yellow. And then we even used a 3rd data set because it gave better information on the Thai islands. So as you can see, this is also quite typical in such a model development. We went from global to national to then detailed. And in this case, the land boundary is relevant also because it determines the, let's say, the end of our model. Our grid ends at the high water mark. In terms of bathymetry, also quite important, you need to have a good representation of the geometry of your area of interest. If you'll have a good tidal propagation and storm surge. We used a combination of several digitized nautical charts from the Royal Navy in Thailand. We used very fine surveys in the upper Gulf of Thailand, and then we combined all of this with the global GEPCO half-a-minute global dataset, which is publicly available. You should keep in mind that you should convert any group of datasets you'll use to the same vertical datum. In this case, we converted them all to mean sea level. And then we show here the tidal stations that we used for calibration validation. On the right, you'll see all these pins, pink and one yellow. Colac is yellow because it was a different data source. But these pins give you an impression of our area of interest. So although we simulated the entire Gulf of Thailand, we were really focusing resolution and calibration effort on the Thai coast along these stations. It is quite a long shoreline that Thailand has, so you want to capture really as accurately as you can the tidal propagation in a long shore. And of course, you should take into account different time zones. So we converted all the data to UTC, although some data sets were given to us in local time zone. It is always worth it to analyze your data for several reasons. We show here some illustration on the right of a storm surge event in March 2011. This is only data, by the way. We're not showing model results yet. So we have the raw data in blue, total water level, and then the tide-only data analyzed in black. So you see for about 12-24 hours there was a surge event, end of March, and then some stations, well, they have a much longer surge signal, we suspect due to sensor issues. Something to be said about the meteorological forcing. This is quite important if storm surge is your topic. So in this model development, we used the operational results from NOAA GFS, 1 degree by 1 degree product, every 6 hours. And the results you need for such a development, it's the wind. From these numerical weather predictions, you will obtain that as the eastward and northward wind components, and then the air pressure, so surface air pressure. So essentially 3 parameters that vary in space and in time. So you should also, even these global datasets, they may have some gaps, which was the case in 2011, but nothing too serious. And then this was what we used for model development. Operationally, actually, we're using the much finer product that I described in the beginning, which is 9-kilometer resolution, much finer. And now I'm starting to show some results of the grid generation. This is quite interesting since we now have the flexible mesh capability in Delft3D. We generated a current grid. This is done automatically based on the depths. So the bathymetry fields that I showed a few slides before, let's say unstructured, almost random positions, you can just load them on this tool, and based on that, we get automatically a current grid. So you'll get resolution that varies with depth in a way to minimize your run times. So essentially this allows for optimal automatically generated grid, avoiding time step limitation. So you can have over deeper waters a coarse grid, in our application 4x4 and 8x8 kilometers, combined with fine grid over shallow waters. In this case, between 500 and 500 and 250 meter resolution. But you avoid time step limitations by doing it like this. So that's a great feature to really minimize your run times. A bit more insight in what kind of grid we are able to generate. Here in the bottom left, you see a map of the region. So it is quite a large model, more than 2,000 kilometers in length. And then it covers quite deep waters there in the southern part of the South China Sea. Goes all the way down to Singapore and then joining to Borneo. On the top right, we show the grid as it is near the open boundary. So you see we go from quite coarse 8-kilometer resolution, and then as the model approaches some islands, let's say, it refines always by a factor 2 in this case, until it gets to the necessary resolution for those depths. In terms of bathymetry, I'm showing here, I have 3 images because we really need different color scales. On the right, we see the deeper parts going down to 3.5 kilometers. On the bottom left, we have, let's say, this intermediate region of the grid, including Vietnam and then Thailand. And then on the top left, you see the upper Gulf of Thailand, and you see the variations in depths that we have. So we have a lot of shallow areas with a depth of less than 5 meters, and you have a considerable part that is quite deep, more than 2 kilometers deep. All of this, again, was converted from different datums into mean sea level. I want to say a few words about the forcing at the open boundaries. We used, in this case, we used Delft Dashboard, another open earth tool option that we make public here at Deltares, Delft Dashboard. You can very easily obtain tidal constituents from the Topex Poseidon Global Inverse Tidal Model database. And it's quite important to get a good tidal forcing in this area. It's quite a complicated area to get your tide right, because you have the tide coming from the South China Sea, you have the tide coming from the, let's say, the Singapore southern part, and there's several amphidromic points in this part. You want to spend some time looking into your open boundaries, and essentially we used, as I mentioned here, 13 constituents. This includes the solar annual constituent, which we obtain ourselves through some iterations. So all the other 12 come from Delft Dashboard, Topex Poseidon. Solar annual we obtain through some iterations. Just for illustration, this is what Delft Dashboard looks like. And we started by creating a rectangle model covering our area of interest, in which in black you can see there are 2 open boundaries. You can obtain quite easily with a few clicks at least the starting point tidal constituents for your simulations. A question that we get very often is, well, how fast does this all run? It's quite useful and important information, especially if you have operational simulations. Delft3D Flexible Mesh not only allows you to optimize the grid, but also allows you to run in several cores at the same time, what we call parallel computing. In this case, we did all our simulations over 12 cores in a Linux in the Linux cluster we have at Deltares. So long story short, we take 1 year to simulate, we take 16 hours to simulate 1 year, or about 9 minutes for the 3-day forecasts. So you get these very fast runtimes by running in Linux, in this case with 12 cores. By the way, there was no special reason we did not use more cores, just because if it takes 16 hours to run 1 full year, we run this overnight and it was good enough. The runtimes can be a little slower depending on which machine you run it and how it was compiled, but this is order of magnitude what you should obtain in your simulations. Keep in mind, this was a very heavy model, with more than 800,000 nodes. In terms of model results, I have a couple slides showing the validation results. Here I show on the left a map with some colors. The green are the stations where we did best. In red, you have a slightly higher root mean square error. And then on the right, you see a table with this summary. Basically, I'm highlighting here the total root mean square error, which on average is just 15 centimeters. Depending on the station, this can be divided slightly differently between tide and surge. But let's say in summary, we could identify the reasons why some stations have the higher root mean square error than this, and it was typically because of local bathymetry issues. Should be said that even those stations with a higher RMSE have a quite high goodness of fit values. Well, that was for total RMSE, and now I have a few slides showing time series. This is the a big surge event in the end of March 2011. This is at the same station, Colac, but we divide in 3 panels. On top is the total water level, in the middle we have tide only, and in the bottom we have only the surge. And in all plots, the black line is observed, the blue line is modeled, and then the dashed pink line is the difference. What I want to show here is that in this station the model does quite well. You can see in the bottom the storm surge goes to 0.5 meter, and it's captured quite well in the model, both in timing and amplitude. Yes, I think this is all I want to say about this station. We can make similar plots for all stations, and you see that there's more noise in this case station PS. You see there's more noise in the surge, in the observed surge, but again quite a good fit with the model result. In some cases the shape of the surge is not exactly reproduced, but the peak amplitude and the phasing is quite well reproduced in the model, although these stations cover a distance of more than 1,000 kilometers along the Thai coast. The previous slide was about that event, so I think the time series showed 2 weeks. Here we're showing the entire year. So we want to show how biased, for example, the results might be for the entire year. So these 2 plots show results at 2 stations, and we have a 7-day average, moving average of the observed surge, of the model surge, and on the difference between these 2. And you can see that there's a bit of overestimation of about 10 centimeters, which tends to 0 for the more important surge events. Essentially, this model was calibrated to reproduce the storms better, and it still does quite a good job over the entire year. This is also something very nice that can be easily produced from the FM software. You see here on the left the co-tidal chart for M2 obtained from the model, and on the right the same co-tidal chart but from literature. You can see the amphidromic point from M2 is reproduced quite well. It's not exactly the same plot, the color scale is the same, but in the model results on the left it's separated, the amplitude on top and the phase in the bottom. You can see the pattern is actually quite well reproduced, including the complicated phase distribution of the M2. This slide I show essentially the same, but for a different constituent. In this case, now a diurnal constituent. Again, there's an amphidromic point near our area of interest, so we want to make sure this was captured correctly. And now I have an animation. Before I hit play, let me go through the images in the bottom. So in the bottom you have 3 moments of the surface forcing, so wind speeds in meters per second. This color scale goes, I believe, to 19 meters per second, so it's already above a weak hurricane strength. So for about 24 hours we had very strong wind speeds blowing essentially west in this region, and this gave those surge results I showed briefly as time series, and I'm going to show you now as an animation. So the animation shows water levels, and you can see that for about 12 hours there are very high water levels in the upper Gulf of Thailand. I'll play it again. So halfway into the simulation you see, let's say, much warmer colors along the Gulf of Thailand. It should be said that 0.5 meter storm surge in this area is quite important because you have a lot of low-lying coasts. So 0.5 meter above your high water is quite important. This slide also highlights the importance of having a big domain. So if it wasn't for the flexible mesh capability, one could be tempted to make a smaller domain, but you see a lot of the wind strength that is then being transferred to the momentum in the ocean is actually coming from quite far from the Thai coastline. It's blowing along Vietnam, but you still want to capture all of that in your model if possible. A few words to be said about something else that you can tweak and calibrate, and you should. Especially if storm surge is your topic, you should take into account that the wind drag coefficient is important. So in these plots, we are showing the effect of varying. In this case, we use the Charnock parameterization, and we wanted to use the same that is used by the meteorological model. Essentially, that's how the atmosphere communicates with the ocean, so to speak. And we tested the sensitivity of this parameter. So you see in the plots on the left, bottom right shows the sensitivity of the surge to varying this parameter. The sensitivity of the tide is almost none, as it should be. So essentially, varying this parameter has an impact on your simulated storm surge, especially when the storm surge is, in this case, greater than 30 centimeters. I think this is my last slide of the hydrodynamics, so I want to highlight the main points. We used the Delft3D Flexible Mesh in the Gulf of Thailand to really do the best that we could to have an efficient and effective model. So we built an unstructured grid model capable of representing tide and storm surge at a sufficient spatial resolution. Sufficient is important. And we wanted these to have manageable runtimes, so to provide the first operational model to run in HAII. Of course, these forecasts need to be of sufficient quality, otherwise warnings issued based on them could be unreliable. So we achieved what we set out to do, and the final resolution is matched with the low runtimes. And overall, we managed to achieve high quality in this first Gulf of Thailand surge model. I think that was my last slide, and now I give the word to my colleague Kunyan.
Thanks, Joel. My name is Kunyan. Hello, everyone. I will continue the introduction of the Delft-FEWS flood forecasting system and early warning system part. As briefly introduced before, Delft-FEWS as software package has been widely used for more than 40 countries in the world. It has been a forecasting system set up for different government agencies in the different countries. Also, the software package has been used by consultancy companies, for example, universities, that wants to set up their own forecasting system. And which worth to mention that Delft-FEWS is a free software where have many configuration options that users can explore freely. And by doing many projects around the world, we also get experience and feedback and input from all the users that contribute to the further development and continuous development of Delft-FEWS. Of course, this time we focus on Gulf of Thailand, which is the system that we are talking about right now. Apart from the international projects, we also focus on the Dutch government-based flood forecasting systems. Here, this slide shows 6 major systems that currently running operational in Dutch government. For example, for the coastal related system, we have the North Sea, which forecasts the storm surge and waves along the North Sea, the Dutch coast of the North Sea. We also have the ensemble forecasting, as well as the data simulation module to do the error correction, therefore improve the forecast. We also have the lake system, which forecasts similar parameters in 2 lakes, Lake IJssel and Lake Marker, in the north part of the Netherlands. Down below, we have the Rhine-Meuse estuary system, which simulates the tidal and discharge from river interactions in this complicated area, and we support the decision of the open and close of the storm surge barrier in that region. We also have 3 inland water systems, such as FEWS River, which simulates the river discharge and water levels from the upstream of the Rhine River basin in start from Switzerland and Germany and all the way to the Netherlands. We also have the real-time control system, which controls water level of all canals and rivers across the Netherlands, as well as the hydrology system. Apart from the practical applications, we also have sort of research-oriented project that funded by Deltares' internal budget that try to explore the capability of our software. For example, here the Global Storm Surge Information System, GLOSSIS, actually provide the opportunity to simulate the storm surge and water levels across the globe, actually in near real time. Here you can see the grid that is based on the Delft3D Flexible Mesh software that global storm surge and water level model has been built based on. You can see here near the coast that the grid resolution are much finer than the offshore area, which gives a nice say trade-off between the computational time and accuracy. So we also be able to integrate this complicated model into Delft-FEWS to simulate storm surge and water levels across the globe in real time. We issue 4 forecasts per day. Each forecast the storm surge for the next 10 days. So in this way, we really try to push the limits of the 2 pieces of softwares to see how they interact and work together. Coming back to the Gulf of Thailand forecasting system, some brief words about forecasting system itself. It always starts from the integration of data. The data that has that can be used for the model input. For example, the numerical weather forecast, which serves the input of hydrodynamic model as well as wave model. We also have real-time water level measurements that was imported in real time into the FEWS system. This data can be used for later model evaluation, for example. And all the imported data are pre-processed by Delft-FEWS into the correct format of each model. Then those data has been fitted into the model and start model simulation. All the models running forecast mode has been scheduled according to a certain time interval in order to issue the forecast, in order to issue the daily forecast. So there is data and forecast management inside the Delft-FEWS software. After the model simulation finished, we can visualize the forecast in scalar time series as well as in grid time series inside Delft-FEWS. But Delft-FEWS can also report or export various data formats to different platforms. For example, we can export HTML type of data, and which can be used on online dissemination. This is Delft-FEWS Gulf of Thailand viewer. You can see here is a GIS-based viewer that shows a map of Thailand as well as Gulf of Thailand. On this viewer, on the top left, you can see the data category that that can be visualized in this viewer. You might not see clearly what's in it, but this is basically a real-time water level observation, numerical weather forecast, the hydrodynamic simulation output, as well as wave model simulation output. And in the middle, you can see all the locations, which is 21 important locations along the coast of Thailand. And then down below, you can choose the parameters that has been computed by these platforms, for example, water level, significant wave heights, wave direction, etc. For example, this is the scalar time series that visualized in the station of Chopaya. Here I plot the significant wave heights as well as the wave direction. Here in the red line shows the forecasting start time, which is T0 of the current forecast. And the data can be also visualized in two-dimensional. So here is the spatial time series viewer, which shows the DFlow-FM water level forecast. And you can play the animation here inside Delft-FEWS by clicking this play button. Here, this timer indicates the time of the output of the water level. You can see also the current system time here down below. Here, this flowchart shows basically the workflow of the FEWS Gulf of Thailand system. So at the beginning, we import the data that are required for the model simulation. Here, as mentioned by Joel, these Wolf Rooms meteorological forecasts provided by our client HAII, which has high resolution, are imported. We also import the globally freely available NOAA GFS meteorological forecast, and these datasets can be served as Plan B if the Wolf Rooms dataset is not available or partially not available. We also import NOAA WaveWatch 3 data for the boundary condition forcing for the SWAN wave model. And after the importing, all the imported datasets are pre-processed to the data format that is required by the hydrodynamic model and wave models. After pre-processing, those datasets has been forwarded to the model simulation folder in order to start the DFlow-FM simulation and two wave model simulations. The two type of models are actually simulated at the same time, where the local wave model are nested in the regional wave model. So which means the after the simulation of the regional wave model, the boundary condition as wave spectra has been forwarded to the local wave model as a boundary condition and start the local wave model simulation. After all the models has been model simulation has been finished, then all the results that we get from the model are post-processed into, for example, wave forecast. We also have a simple static inundation module to calculate the on-land inundation near Bangkok. Meanwhile, we also import real-time water level from the water level stations near the Thai coast. We also export the model results into various formats that to be disseminated later to various platforms. So we believe this forecast system actually contribute to HAII's existing daily forecast report. Our forecasts are run every single day, so every 24 hours, and the forecast horizon, which also the lead time is 3 days. So here on the top, you can see the Wolf Rooms meteorological forecast data provided by HAII on a daily basis that has been imported into Delft-FEWS viewer, and this data set is with 9 kilometers resolution. On the bottom, there are also this is also the NOAA GFS, the global forecasting system meteorological forecast that imported daily by Delft-FEWS, and this is a quarter-degree resolution. So as I said before, this NOAA GFS forecast has served as a backup meteor forcing in case the wolf rooms is partially unavailable due to whatever the reason. So for the states handling part, that on the top, you can in the figure you can see the model first simulate a handcast for the last 24 hours, and then start a forecast for the next 72 hours. And the forecast always start from the warm states that provided by the handcast simulation. And the handcast is actually start from the warm states provided by previous handcast simulation. So in that case, if say due to whatever the reason, for the last 48 hours there is no forecast available, then the handcast will automatically start from a cold states. Down below you can see the in the video that I'm going to play, this is a full forecast simulated by the D-Flow FM hydrodynamic model. This is well, not an event, but a 4-day forecast from the last year of December. And then here down below you can see also the forecast overview from the thumbnails, that every 3 hours it provides sort of overview of the forecast. Okay, I'll move on. For the wave parts, here you can see on top is the regional wave model forecast. In the middle is the local wave model forecast, which are nested in the regional model. So we provide 3 parameters: significant wave heights, mean wave period, and mean wave direction, that can be visualized from the Delft-FEWS viewer. And down below you can see the wave setup that calculated in Delft-FEWS along the Thai coast. Here SWAN doesn't directly provide the wave setup calculation. So based on the wavelengths and wave period calculated by SWAN, we use empirical equations to calculate wave setup on different locations along the Thai coast in Delft-FEWS. Then we aggregate to a grid data set, which is visualized in the below figure. We also calculated a simple static inundation module here in Delft-FEWS. This inundation is actually based on the water level forecast at 4 locations near the Chopaya estuary. That we take the scalar time series of the water level forecast from D-Flow FM. We integrate them into a grid, which is shown in the viewer. Then we use a PC raster module to subtract the underlying DEM by using this water level 2-dimensional area. So here is a video showing the flood inundation area that calculated by this static inundation module based on PC raster, which is also fully integrated in the Delft-FEWS software package. After we get the model results, we export the results into various formats. For the scalar time series, we export it into charts for every single location and for every parameters. For the 2-dimensional model results, we exported every time step as image, saved as PNG or TIF formats. We also save the forecast as animations into GIF format. We can also export all the raw data of the model output into nested files for later, for example, model evaluation purpose, etc. And these animations can also be saved in HTML format that can be disseminated online, by which is actually now the case by our client HAII. Okay, I guess this is the last slide of my the FEWS part presentation. So in conclusion, we have shown that the new early warning system to predict the coastal flooding levels along the Thai coast. This system, now used by the Hydro and Agro Informatics Institute, provides 3-day forecast generated daily, combining effects of tide, storm surge, and wave setup. So what's now that HAII is operating this system in real time independently. Given the fact that Delft-FEWS provide the easy plugin options of different modules, HAII might consider to include other new nested models to represent, for example, smaller estuaries or even water quality models to provide water quality forecast. So why was this project a success? That we think one word is very important, which is flexibility. Because our client, HAII researchers, are very motivated. They'll help us a lot during the whole modeling process and the system build-up process. They are also very capable during the training. Our software package, Delft3D Flexible Mesh, allows for optimal configuration, grid resolution, and run times. Our software package, Delft-FEWS, is also a modular based software that allows for tailor-made solutions that be able to run all kinds of different external models and allow different data exports. So that's the end of our presentation. Thank you very much for your attention.